So we are now recording this, and I'm going to put the lectures up afterwards also on the course homepage. Let's just go through a bit about the what the course is all about. So you are going to be essentially two groups of students, and it's going to be the course SI 1142, not 46 as I wrote in the lecture notes. It's a different course. And this is also a part of SI 2360. And the SI 2360 is actually 12 double hours of lectures, not 6 as I wrote in the lecture notes. And out of these, in the second course, I will be giving 3 of the additional lectures on symmetries. After this lecture, you will have an exercise class with Linda, who is a new PhD student here, and that will be in a different Zoom room. And in general, well, you can read in the course lecture notes. These lecture notes are available on Canvas. Essentially, what the course is about. The first module, which is also SI 1146, is about how we can introduce coordinate systems, how we can use arbitrary coordinate systems, and also how we can use them to describe more general spaces than Euclidean space. For example, curved spaces as the sphere you see down here. And also we're going to apply this to the Lagrange formalism for classical mechanics. And we are going to go also a bit deeper into the so-called Hamiltonian formalism of classical mechanics, where we will be using with what is called phase space instead of configuration space. The future applications of this include things like relativity, both the special theory and the general theory. And you can also make advanced analysis of classical and statistical mechanics. And there are some generalizations to quantum physics. And in the second part of the second course, so of the master level course, Edwin will talk about the relation between the Hamiltonian formalism and quantum mechanics. And the aim of this course is, in essence, that you should be prepared for the higher level studies of theoretical physics. So that being said, let me get into the subject matter. So I'm going to start to talk a little bit about coordinates. So the question is, what are coordinates? Well, if we start in our Euclidean space, you know that well, I will have a hard time drawing in more than 2 dimensions. But if we have 2 dimensions like this, you have the x and y axis. Essentially, if you have a point in this space, you can describe this point by the x coordinate and the y coordinate. Now, this is not the only coordinates that we can use. We can also use polar coordinates here. In that case, we would have r as the distance between the origin and the point, and we would have an angle here, which we can call phi. So either of these descriptions, giving either x and y or r and phi, will give you a unique description of this point here, which we can call P. So in general, a coordinate system that's a number of functions and in general I'm going to call them chi with an index a, where a goes from 1 to n, where n is the number of dimensions, that uniquely describe a point. So if I give you the values of all of these n functions, you're going to know which point I'm referring to. So for example, if I give you the values of r and phi, you know that I'm referring to this point P here. And as I said, examples are these, for example, in this case, Cartesian coordinates x and y, or the polar coordinates r and phi. In addition, we also can introduce a couple of basis vectors. So if I have a vector at any point here, if I have a vector at my point P here, vector V, a vector basis is going to be, in this case, two vectors, since I'm working in 2 dimensions, such that I can write any vector V as a linear combination of those two. And given a coordinate system, I can introduce two different bases based on those coordinates. So the first one that I can introduce is the so-called tangent basis, which I'm going to call E with a sum index I. And I define that as the partial derivative of the position vector with respect to chi I. So the position vector here is nothing else than the vector that translates you from the origin to this point. So in this case, this vector. And this is the tangent basis. The other basis that I will introduce is called the dual basis. And I'm going to write that with an index upstairs instead. And I define that as the gradient of the coordinate functions. So either of those bases form a complete basis at every point. So that means that given a vector V, I can expand this vector in either the tangent basis, which I will write as VI EI, or in the dual basis, which I will write as VI with index down and EI. So is everybody familiar with the notation I used here, which is the Einstein summation convention? If there is anyone who's not familiar with this, well, I will say it anyway. So this summation convention here, that is that if I have two indices that are the same, those indices should be summed over the available range. So what this actually means is that this is equal to the sum over I from 1 through n of this expression. And the same thing for the right-hand side. So just to mention that these components here, the VIs with the index upstairs, are called the contravariant components. Of the vector V. And these components with the index downstairs, so the components in the dual basis, they're called the covariant components of this vector. So just to give an example of this, in polar coordinates, we have the following. So the tangent vector basis, ER, this was defined as the derivative of the position vector with respect to R. And the position vector, that's x E1 plus y E2. And if we rewrite this in polar coordinates, we'll get R cos phi E1 plus sine phi E2. So if I insert this here and I perform this partial derivative, what I'm left with is going to be cosine phi E1 plus sine phi E2. That's just differentiating with respect to R here. And if I do the same for the phi coordinate, what I will find is that this is r times minus sine phi e1 plus cosine phi e2. So if I'm going to draw this now, if I draw the ER in red here, what I have is a number of, it's a vector field that's pointing essentially away from the origin. And if you take the norm of these vectors, you will see that it's 1 because of the trigonometric 1. And if we write the phi vector in blue, that's vectors that are orthogonal to those radial basis vectors, looking something like that. So we have E phi and we have ER. And as you can see here, at every point, these vectors form a basis, so you can expand any vector in terms of them.
A quick question.
Yeah, sure.
The definition of a coordinate system, is it only for Euclidean space?
It's going to work also it's going to work for any space. The difference is, if we go back to this, is that it only needs to work for a part of the space you're describing. So for example, on the sphere, you're not unique in the sense that if you take the typical spherical coordinates, if you let phi go from, I mean, it's 2 pi periodic essentially. So it's not unique in that sense. But if I tell you that this is the range and it doesn't cover the entire sphere, but it just covers a subset of the sphere, then it's going to uniquely map 2 values to a point in your space. So for example, the sphere then.
Okay.
So, well, let's take an example on that actually. So let's take the sphere in 1 dimension. So that's the circle, right? So here you could use a coordinate which is essentially if I take this point here, I can use this angle phi as the coordinate. Now, if I let phi go from 0 to 2 pi, I have a unique mapping to the circle. What I do not cover is this point here, but then I can introduce a different coordinate system. For example, I can choose the same angle but call it phi 2, so phi 1 and phi 2. Now these are different coordinate systems. Let me be more consistent in what I write. But I can let phi 2 instead go from minus pi to pi. So in that case, I would not cover this, but together, both coordinate systems cover the entire circle. But the only necessity is that they are locally unique. So if I am here and I'm looking at the coordinate system around that, in that small range, it should be a unique mapping to the circle. Any more questions? Just interrupt.
I have one question.
Yeah, sure.
Can you hear me? If you go back to the previous slide, is there any specific reason why these components are called contravariant and variant and covariant?
Yes. So essentially, the co and contra refers to whether or not to their transformation properties. So as you can see, if I change these coordinates chi, if I go to a different coordinate system, I will clearly not have the same basis vectors. But since the basis vectors of any coordinate system is complete, I can expand them in each other, and that's called the coordinate transformation of the basis vectors. So covariant essentially means that they transform in the same way as the tangent basis does. So the tangent basis, if we just look at that, so that's a good side. If we look at the tangent basis, we had that EI was equal to dx d chi I. Now, if I just use the chain rule here, and if I have a different coordinate system, I can write this as d chi prime I prime, where the chi primes are my new coordinates, d chi prime I prime d chi I. Now, if you just look at the definition of the tangent vector basis in the prime system, this is just that. So this is E prime I prime. So this means that this is equal to this partial derivative of the coordinate functions times E prime I prime. So this is the transformation rule between the tangent vector basis in the unprimed system and the tangent vector basis in the primed system. So something that transforms covariantly is something that transforms exactly like this. Something that transforms covariantly means that essentially we change the position of these two in the partial derivative. And that is going to be exactly how the dual basis transforms. So that's where the nomenclature comes from.
Okay, thank you.
And another point with regard to that is that you see that we have, when we have the tangent vector basis which transforms covariantly, we have contravariant components. And since they transform in the opposite way, if we just look at this, VI EI, this is going to be VI prime d chi, let me use a different index, j d chi prime j prime, and then we need to use the transformation rule for this guy for the tangent basis. That would be d chi prime. Let's use it's going to be j prime. No, sorry, I screwed up this one. It should be an I prime. And j prime there, and then the chi j. No, sorry again, this should be an I. This should also be an I, and for the transformation rule of those, I should have a j prime. Now, this guy, just because of the chain rule, is the chi prime j prime d chi prime I prime, which is just delta j prime I prime. So it's 1 if I prime is equal to j prime, which means that this is the I prime E prime I prime. So you see that the expression for the vector v is the same in both coordinate systems. It's the contravariant components multiplied by the tangent vectors, and it was this fact that they both transform in the opposite way that made it this way. Okay, so also let me say that in general what I write here is going to be very similar to what is in the lecture notes that you can find on Canvas already. So another thing that is related to what we just said is the following, that if we have in general this EA and we take the inner product with EB, or for that matter EA inner product with EB, these are not orthonormal vectors necessarily. These are not necessarily equal to delta AB. And it's only going to be true in what we call an orthogonal coordinate systems. However, we have the following relation, that if we take the dual basis vector EA and take the inner product with the tangent vector basis EB, this is the gradient of chi A inner product with dx d chi B, and this again is the chain rule. So this is equal to d chi A d chi B, which is just delta AB. So while these vectors do not necessarily form orthonormal bases, we have the fact that the tangent basis and the dual basis are defined in such a way that if you take one of them and multiply by the other, you get this delta. And we can use this if we want to know the components. Of a vector v. So for example, if I have a vector v, I know that this is equal to vi ei. If I want to know what this component is, what I can do is that I can multiply by on both sides by this ej. And since ej times ei is this delta, this is equal to delta ji vi, and then I have the sum here because I is repeated. So this is equal to delta to vj. So I can get the jth contravariant component by scalar multiplication with the dual vector ej. So just as an example of that, let's look at the position vector. In polar coordinates. Now, if I compute ER, you will find that that's just the same as ER with the R downstairs. So this is sine phi E2, and E phi is 1 over R minus sine phi E1 plus cosine phi E2. So you know that the position vector in polar coordinates, well, we knew what it was. We wrote it down before. It was this R cosine phi E1 plus sine phi E2. So if I now want to know the R component of this, so the contravariant component in the R direction, I would take this ER and I would multiply this by X. And as you will see, this first term will give you cosine squared. The second term will give you sine squared. So that's 1 multiplied by R. So this is just equal to R. And in the same way, if you compute the phi component, this would be E phi scalar X. And since this vector is orthogonal to this vector, you will end up with 0. And this then means that if you want to write the position vector in polar coordinates, it's given by R times ER plus 0 times E phi, which is just RER. Any more questions so far? Okay, so let's continue then. And what I want to discuss now is the concept of tangent vectors. So I already talked to you about what the tangent vector base is. Now, why is it called the tangent vector basis? So essentially, we took the derivative of the position vector with respect to the coordinates. But in general, if I have some curve like this, that curve is essentially that if you have a parameter t along it, that curve is essentially a map from a single parameter t to the space that you're looking at. So you can do this. You can describe this by giving all of the coordinates as some functions of this curve parameter t, and equivalently, you can see the position vector then as a function of t, where now t is this curve parameter. And we define the tangent vector of this curve as the derivative of the position vector with respect to the curve parameter. So again, our favorite relation here is the chain rule. So we can rewrite this as the derivative of the position vector with respect to the coordinates times derivative, sorry, it's a total derivative. The derivative of the coordinates with respect to time. And this, just for future notation, I'm going to use a dot to denote this. But this we already know what it is. What we have in front here. This is just the tangent basis vector. So this is chi dot a times EA. So for any curve, the components or the contravariant components of the tangent vector are the derivatives of the coordinates with respect to the curve parameter. So these are the components of the tangent vector. And so this means that if I have a point here, if I look at this point, the tangent vector is a vector that points along the curve. And if I call the curve gamma, I'm going to call this gamma dot. So just as an example here now, we can take a spiral. So a spiral looking something like, well, let's see if I can draw something like this, where we have our coordinate system locked in like this. Now in polar coordinates, I can give r as a function of t as some r0 times t, where r0 is a constant. And I can write phi of t as some other constant omega times t. This would describe a spiral like this. And in this case, I would get r dot is just the derivative of r with respect to t. So that's r0. Phi dot would be the same, but with respect to the derivative with respect to t is omega in this case, which means that the tangent vector, this gamma dot, would be equal to r0 er plus omega e phi. Sorry, I used phi this time. Any questions on that? Okay. So as we're going to see later, this is one type of vector that's going to be quite important. So the tangent of different curves. A different type of vector that is going to have physical importance is gradients. So if tangent vectors in essence describe how you move on something, how this curve moves along in your space, gradients are instead going to tell you how a function changes in the space. So essentially in which directions this function grows. So if we take a scalar function, so consider a scalar function f. So this just means that I have a function f that is a function essentially of the coordinates in the space. If I have such a scalar function, I can take the gradient of f. And this is, if we use the chain rule again, is df d chi a times the gradient of chi a. And just as for tangent vectors, where we had this relation over here, for the gradients, this guy, this gradient of chi a, that's our definition of the dual vector basis. So this is equal to df d chi a times ea. So whereas tangent vectors were naturally described using the tangent vector basis, gradients are instead naturally described using this dual basis. And this is going to be important later on when we go to different spaces. And let me just write this as, using a new notation, I will write this as dA f EA. So these derivatives of f with respect to the coordinates are natural covariant components, whereas these derivatives of the coordinates with respect to some single parameters are natural contravariant components. Now we can use this in the following way. So if we want to know the rate of change of a scalar function, so we have some scalar function f, and I'm going to just draw some level curves of f here. So this is f equals to f1, f equals to f2, f equals to f3, and so on. Then you know that the gradient of f is essentially these vectors. And then we take some curve, like this, gamma, with some curve parameter t. And I want to know how does f depend on t. Now, the rate of change of f is just the derivative of f with respect to t. But f depends not on t explicitly, but f depends on the position. So this is the f d chi a. Again, we are using the chain. Total derivative chi a dt, which is this dAf times chi dot a. Now this in turn is then, of course, equal to the gradient of f inner product with the tangent vector of gamma. So this is what's going to describe how the function f changes along this curve gamma. And many of the quantities that we're going to encounter, many of the inner products that we're going to encounter in physics are going to be exactly of this form. So just take an example of that, which fits down here, is the change in potential energy. So if you have the v dt, now I'm going to let t be a curve parameter, which is time. The change in the potential with time, I can write that as the gradient of the potential times dx dt, which is essentially equal to minus the force, because the force is the gradient of the potential with the minus sign, and the x dt in that case is the velocity, if I let t be time. So this is essentially telling you that the change in the potential is minus the force inner product with v, which is essentially the work done per time. We have 6 more minutes before the break, so are there any questions at this moment?
Not about this specific thing, but earlier, would you mind explaining the index convention for the Kronecker deltas?
Yeah, okay. So why, do you mean why I'm using one up and one down?
Yes.
So in general, you should not move indices around. And we will see later that the Kronecker delta is essentially what is called a 1-1 tensor. This means that you can either use it to map like I have here. I have I am contracting this contravariant component with the I here, and I'm getting a new contravariant component. Well, it's the same since it's the delta. And that's essentially it. And I mean, the delta is this thing over here, right? And there I have one index up and one index down. It's, if you take, for example, in Cartesian coordinates, you know that you have this delta ij, and it doesn't matter which coordinate system you go to. But if you go to curvilinear coordinate systems, this will no longer be true. So it's something that we're going to encounter next hour, I think, when we're going to discuss tensors. We're going to encounter the metric tensor. So, but I mean, in essence, it's this guy is for now how we define the delta.
Thanks.
So in the remaining 4 minutes, I'm just going to briefly discuss general spaces. So what I discussed now was Euclidean spaces. Everything was related to Euclidean spaces. Now, in a general space, as we already discussed, because we discussed a little bit about coordinate systems on general spaces, we can still introduce coordinates. Now, they don't need to be global in the sense that they can describe the space everywhere. They can just be local, as we discussed, for example, on the sphere or on the circle. So, for example, on the sphere, you would have some coordinate theta and some coordinate phi, if you want to describe that point over there. So we can still introduce coordinates, and we can describe a point in the space by coordinates. One difference, and I'm not going to go too deeply into this, but one difference is that the tangent space and the dual space are going to be different. So they are no longer going to be the same vector space. I'm not going to do, as I said, not going to go too deeply into that. But let me just say the following, that tangent vectors will still have contravariant components. So a tangent vector will again be the chi-a dt is going to be the components of a tangent vector. I'm not going to go into too much detail of what the basis actually is here, but the basis is going to act in the same way. It's going to have very similar properties to the basis that we had in the Euclidean space. Dual vectors will have covariant components. So for example, the gradient of a function f, which I will call df, is going to have components dA f, which as before is just the derivative of f with respect to components. And again, I'm not going to go into too much detail of what these bases actually are. It suffices to say that they act in a very similar way. However, the rate of change is still going to be the same. It's still going to be that df with respect to derivative with respect to t is going to be chi dot a times daf. It's the same chain rule. And we can write this as gamma dot scalar product with df. So in essence, what these dual vectors do is that they map tangent vectors to real numbers. So you can see the dual vectors as a rate, as how the function changes, and the tangent vectors how you move along in this space. It's 2 o'clock, so we're going to take a break of 15 minutes unless there are more questions at this point.
Would you mind repeating the very last thing you said about the?
Yeah, so about the rate of change.
Yeah.
Yeah, so the rate of change is just as we had here in the Euclidean space, where we had this expression for the rate of change. That expression is still valid. So it's still going because it's just a chain rule. So if I look how f changes with respect to the curve parameter, that's still going to be given by this same expression, which I'm just going to call the inner product between this tangent vector and the dual vector.
You also mentioned something about interpreting the dual vectors. What was that? Or do I misremember?
I don't know if I said interpreting the dual vectors. What I said was that I'm not going to go into too much detail of what the actual bases are. So, I mean, that's something we don't really need to know at this point. All I want to say here is that the basis is similar, has similar properties to the basis that I introduced in the Euclidean case.
Okay.
If you really want to know what they are, but this is not going to end up on the exam. The basis vectors here for the tangent vectors are partial derivatives, because if you remember in the case of Euclidean space, we had this relation, right? Dx d chi a. This was our definition of EA. But in our general space, there is no position vector. There is no position vector on the sphere. if we see the sphere as a two-dimensional object. So what doesn't exist in this case is this position vector. So it is in some sense natural to have these partial derivatives as the basis, and due to the chain rule, they are going to transform exactly as these tangent basis vector transform. But that's a bit extension of what we're going to discuss in this course.
So basically what you mean is you're not going to introduce the basis vectors and how we define them, but what you've done is you've defined the coordinates and how they change. So they're basically the same as previously.
Yeah.
But yeah, okay, I get it.
So
Thanks.
so I mean, if you want to know more about this, I mean, there's the GR course later on, where I discuss this a little bit more. And if you want to know more about it, it's also in the in my book in chapter 9, I think. So I didn't say about the course literature because there are many course literatures. So I mean, one of them is my book. It's this thick, but it's not all included in the course, of course. There are reading instructions, and you can find that to download for free. You can find the PDF on the KTH library. Okay, so it's 2:16, so let's continue. I hope everybody's back. So let's see. We have discussed now for the first hour, we have discussed coordinate systems and vectors. So what I will be discussing for this hour is tensors. Now, what's a tensor? Does anybody have a intuitive feeling of what a tensor is?
I mean, formally it's multilinear mapping.
Exactly. Good. So we don't need to have this course. No, but there's always someone who says that the tensor is something that transforms as a tensor, which is often what you hear in introductory courses. I do not want to take that approach because I'm going to take the approach that you just said, that I'm going to look at tensors as multilinear mappings. So let's just check what this means. But first of all, let me give the formal definition. So a tensor of type NM is a multilinear mapping from M tangent vectors and N dual vectors to real numbers. Now, so multilinear, what does it mean? So in general, a tensor of type NM is going to have N plus M arguments, and N of those arguments are going to be dual vectors, and M of those arguments are going to be tangent vectors. So for example, if we take a tangent vector, and I'm going to assume that it has components VA in some coordinate system, and I ask what kind of scalar can we construct from this? Well, we could take this tangent vector and we could create the following scalar if we also have a dual vectors. So given a dual vector, I'm going to call it omega, and I'm going to put the index down. Then VA omega A is a scalar. It's a real number. Now this mapping, so from omega, if I take V of omega to be this VA omega A, this mapping is linear because if I put V of, well, let's say K omega, K1 omega 1 plus K2 omega 2, this is equal to, and well, it's just the sum is linear. So this is K1 V of omega 1 plus K2 V of omega 2. So this is linear in the argument omega. So this vector VA, or with the components VA, can be seen as a map from dual vectors. It takes one dual vector as its argument, and it maps it to a real number. So this means that it maps one dual vector and 0 tangent vectors to a real number. So that means that tangent vectors are type 1 0 tensors. Now, in the same way, I can see this not as a linear map of omega, but of V, because it's linear also in V. So this means that dual vectors are type 0 1 tensors. Because given a dual vector, I can map a tangent vector to a real number. And multilinear just means that if it takes several arguments, it's going to be linear in each argument separately. So does anybody know about more examples of tensors without looking in the lecture notes?
The moment of inertia tensor.
Yeah,
right.
The moment of inertia, for example, that's a physical example of a tensor. I will come to physical examples in a moment, but just to say that in that case, it's a little bit different because then you have a mapping from a vector to a vector. So the moment of inertia maps the angular frequency of a rotation to the angular momentum. So that's a mapping from a vector to a vector. Now, it turns out that is the same thing essentially, that because then you have a vector which is a mapping from dual vector to real number. So it's essentially the same. An alternative form of this that I wrote up here is that you map a that if you see 0M tensors as maps from vectors to from M vectors to real number, then a type NM tensor is a map from 0M tensors to 0N tensors. But let's not go too much into that. But it's clearly another example. The example I was thinking of is, do you know? Well, let's work in Euclidean space to start with. So, do you know something that takes two vectors and gives you a number?
The inner product.
The inner product, exactly. So the inner product, I mean, that's a tensor, or it's related to a tensor because it's linear and it takes two vectors. So I'm going to call it, if we take V scalar product with W, I'm going to call it G of V and W. Since this is linear in both V and W, this function is going to be a tensor, and it's going to be a 0-2 tensor because it takes two tangent vectors and it gives you back a number. Now, let's look at what is called tensor components. So let's remember this tensor for later. So this is called the metric tensor. So let's just briefly discuss what tensor components are. So I'm going to discuss it in Euclidean space, but essentially the formalism is going to work exactly the same in general spaces as well. So let me take a tensor of type n0. So for example, if n is 1, I could take a tangent vector. Then I can ask myself, given a basis, given a coordinate system, how does this work on the basis vectors that we had defined earlier? In this case, on the dual vector basis. So we define then the components of T as Ta1 through An as how this tensor acts on the basis. So Ea1 through Ean. So note here that what I put into this tensor are the dual vector bases, because this T was a tensor of type n0, so it should take n dual vectors as arguments. Now I can do the corresponding thing for for 0m tensors. In that case, I would have T b1 through bm, and instead of putting the dual basis in here, I would put the tangent basis in here. And also, if you have an nm tensor, you would put n dual vectors in of the dual vector basis, and you would put m of the tangent vector basis in, and then you would have so-called mixed component with both indices up and down. So, for example, if we look at the metric components, if we look at the metric components, so this metric tensor that we defined over here, so we have the metric somewhere, we have this metric which is defined as the inner product between the two vectors. It takes as argument. So in this case, if I look in Cartesian coordinates, then my basis vectors are the Cartesian basis vectors. So if I take G of EI and EJ, that's EI inner product with EJ, which is delta IJ. Now in Cartesian coordinates, it doesn't really matter if I put the indices up or down, and that's because of how Cartesian coordinates work. However, if I go away from Cartesian coordinates and instead I look at polar coordinates, then all of a sudden the components of my metric tensor, which I define as this, that's the inner product between EA and EB. Now in curvilinear coordinates, this does not need to be an orthonormal system. So this inner product does not need to be the Kronecker delta. And this by definition is the component GAB. So if I want to have the GRR component of this tensor, that would be ER inner product with ER. Now that happens to be 1. If you go back to when we computed the tangent vector basis here. However, if I take G phi phi, that's E phi, E phi. That's no longer 1, that's R squared. And finally, G phi R, which happens to be equal to GR5 because the inner product is symmetric. That's ER inner product with E phi. And since polar coordinates are orthogonal, this is actually equal to 0. So these are all the 4 components of the metric in polar coordinates. Now yet another example, and because we have discussed this already. So we briefly mentioned now that that the tensor can also be seen as a map from vectors to vectors. What's the simplest linear map from vectors to vectors that you can imagine?
Matrices.
That's more general than what I actually had in mind. if you want a specific one, what is the simplest specific linear mapping that you can construct?
Identity.
Yeah,
maybe?
the identity. The identity maps a vector to another vector, the same vector, but it's an identity transformation. Right? Do you hear me? Because it's warning me about some microphone issues.
Yes, we
Yeah,
can
we
hear you.
hear.
Good. So the identity map, which takes a vector and maps it to itself. Now this is interesting because this is a 1-1 tensor. Because it maps a vector, a tangent vector, to another tangent vector. The question is, what are the components? Well, let's look at that. So the components of a tensor, if I take any tensor, T of V, that is a 1-1 tensor, this should be equal to T AB VB. However, for our particular identity map here, this is equal to VA. And this means that TAB is just the Kronecker delta. Because if you let TAB be the Kronecker delta, you get exactly this property, right? So this actually answers the question, why do I have the indices of the delta 1 up and 1 down? It's because the delta is actually a 1-1 tensor. And it corresponds to the identity map. Okay, so let me just briefly go just to the lecture notes. So just to give you a few more examples of tensors. So as someone already said, the first example I have of a tensor is the moment of inertia, because you have the angular momentum, the omega. If you have something that's rotating, you have the angular momentum omega, and you have the angular frequency omega, and you have the angular momentum L. And the moment of inertia is a linear map between the angular frequency and the angular momentum. So it's linear because if you spin in the same way but just spin faster, you're going to get a proportionally faster, a proportionally larger angular momentum, and so on. Other examples include the stress tensor sigma, because essentially that relates a surface element, which is a vector, to the force, which is also a vector, across that surface element. So that maps a vector to a vector. The electric field is also a tensor field because it maps, well, nothing, a scalar, to a vector. But that also makes a scalar is a tensor of type 0, 0, because it's just a real number. It maps 0 vectors to vectors. So the electric field which maps charge, which is zero tensor, to the force, that's a 1, 0 tensor. And then you have the magnetic field tensor. I mean, you have the magnetic field too, but the magnetic field tensor maps the velocity to a force. So if you have a charged particle moving in a magnetic field, you know that the force here is Q times V cross B, and that's a linear function of V, so it's related to a 1, 1 tensor. And if you want to go to higher order tensors, like a second rank tensor, for example, you can look at the strain tensor in strength of materials, which essentially describes for you, it's a rank 2 tensor which describes for you how a material is deformed. And actually, if you consider the relationship, the more general relationship between the strain, so it's how a material is deformed, to the stress, which is the internal forces in that material, that's Hooke's law, which you might have seen the one-dimensional version of, that in a linear way relates the strain to the stress. And since they are both rank 2 tensors, this relationship between them is a type 2 tensor. So that's a rank 4 tensor used in strength of materials. And it's interesting because the other rank 4 tensor that I'm familiar with in physics is the curvature tensor of space-time, which describes how space-time curves. But we will not go into that in this course. So these are just a few examples of tensors. So with that, I'm going to go back to what I'm writing. Are there any questions so far?
Yeah, I had one. Can you go back to the previous slide, please?
Or the one with the tensors?
No, sorry, the one with yeah, exactly this one. The permutation symbol.
Yeah.
Is that a tensor?
Yes and no. So in Cartesian coordinates, it's the components of a tensor, or a pseudo tensor, because if you change the handedness, it changes sign. It's a little bit tricky. However, in more general coordinates, it's not going to be a tensor, but what is called a tensor density, which means that the components transform a little bit differently. So if you multiply by the square root of the metric, determinant of the metric, then it's a tensor. But
Okay.
we will not go into much detail about that. If you want to read more about it, it's, I think, in chapter 2 of my book. It's described there, but it's not. We're not going to discuss it in the course.
I also have another question about this, and it's about the electric field. So you said that was a 0, 0 tensor?
No, sorry, 1, 0 tensor.
Okay, it's a 1, 0.
I mean, the charge, for example, is just a scalar. So it maps a scalar to a force.
Right. Right.
So that's a 1, 0 tensor.
Oh yeah. Okay. Yeah.
I mean, it maps a 0, 0 tensor to a 1, 0 tensor. So it's a 1, 0 tensor.
Yeah. Thanks.
Any other questions? If not, I'm going to continue with the next issue, which is going to be the covariant derivative. Oops, I should remove. If you wonder why I'm making perfect circles when I'm making circles, it's not that I make perfect circles, it's that there is a tool for making circles. And you can't write with that tool on. So what I want to discuss is called the covariant derivative. Now, in Cartesian coordinates on Euclidean space, you have a basis vectors that are fixed. So your basis is the same at every point. However, that is no longer going to be true if we look at the curvilinear coordinate system. So this means that in the Cartesian coordinate system, essentially the partial derivatives are going to let you describe tensors in general. But we're going to see that it works a little bit differently in curvilinear coordinates. So in essence, if I have, let's say, a vector basis at this point, and I have the same vector basis, but at a different point, sorry. So I have 2 points, and I move between those points, and I have a vector that I want to describe using this basis. We can call this vector V. Oops, did not want to cut it out. I wanted to duplicate it. So, well, that is parallel to the red vector, is just a coincidence. So this vector is the same. However, at this point, it's parallel to the red basis vector, so its blue component is going to be 0. But at this point, it's not parallel to the red vector, and it's going to have a component in the blue direction because of that. So this means that the components, even though the vector is constant, are not going to be constant. So in order to describe this, we're going to introduce what is called the covariant derivative. That is going to essentially mean that we're also describing the change in the basis, just as we have drawn here. So let me introduce the following. The following derivative. So let me look at what the derivative in the A direction of the bth tangent vector is. Now, EB is a tangent vector field. It depends on the point where I am. And I'm just differentiating that with respect to chi A. So what I'm getting back is a new vector field. I'm getting the vector field that is telling me how this vector EB changes with a point. Say, for example, if EB is this blue vector here, it's going to change from one point to another. And so it's going to be a new vector field. So it's going to have the property that I can expand it in components. In particular, I can expand it in the tangent vector basis. So let's do that. It's going to be some linear combination of EC, and the components of expansion are going to depend both on which A and B that I choose, but it's also going to have an index C. So this is going to be true for some gamma CAB. And these gammas are called Christoffel these are called Christoffel symbols. Now, we talked a little bit about this. How am I going to get what these Christoffel symbols are? How am I going to get an expression for them in Euclidean space? Because right now I'm working in Euclidean space, but the expression is going to be the same later on in more general spaces as well. So the question is, how do I get this contravariant component out of this vector field? Any takers? We discussed it during the first hour, how we could take out the components here.
Maybe multiply by a dual basis vector.
Yeah, exactly. So if I want to have the components of this vector, I should the contravariant components, I should multiply by the dual basis vector, which we saw earlier. So I'm going to take ED, and I'm going to take this DA EB like this, which if I do the same on the right-hand side, is ED gamma C AB EC. Now the inner product is just linear, so I get ED, inner product with EC, which is delta DC, gamma CAB, which when I perform the sum over C is just gamma DAB. So that's how I can get these components out. So I can now use this if I want to describe the derivative of any vector field. So for any vector field, and let's call it V, we know that we can expand it in terms of components, in terms of the tangent basis. So I'm going to write it as VA EA. If I want to know how this vector field changes from point to point, then I can look at the partial derivative. So let me look at dB acting on V. So this is the change of the vector field V in the direction, in the B direction. Now, just writing this out in terms of the components, looks like that. And I can now use the product rule for derivatives. So this is dB VA times EA plus VA dB EA. Now, the first term here I cannot do much about. I will keep it about as it is. I'm going to write it as dB EA again. But the second one I can do something about. This is VA, and then I have this relation up here, just exchanging the roles of B and A. So this is actually gamma B A C times E C, right? And now we have a sum over A and we have a sum over C. We can change, since these A and B are just dummy variables, we can change the roles of them. So I can put the C here, the C there, and then A there, and then A there. Which means that this is equal to dB VA plus gamma B C A VC EA. And this thing here, the component here, is what I'm going to call nabla B VA. It's the contravariant derivative, sorry, covariant derivative. It's the covariant derivative of the vector component VA in the B direction. So what does it mean? So if we look at what the different terms mean here, if you look at the first term, it's telling you how the components change when you move around. So if you go in the B direction, how much does the A component change? That corresponds to if we had a fixed coordinate system, a fixed basis, that would be it, because all the change would be encoded in the coordinates. However, if we don't have a fixed coordinate system, then the basis vectors change, which means that these gammas, the Christoffel symbols, are non-zero. So in essence, the first term here describes the change in V due to the change in the components. Whereas the second term here is the change in V due to the change in basis. the basis itself. So for example, in the example we had up here, where v was the same in both points, the derivative of b, well, that should be 0, even though it has different components. As we saw, in this point it just had a red component. In this point it had both a red and a blue component. That means that in this particular case, those two terms are going to cancel out and give you 0. And one thing to note is, of course, that the Christoffel symbols do not depend on the vector v. It just depends on the coordinates in the basis. Any questions on that so far?
I have a question about interpreting the indices at the Christoffel symbol. So
yeah.
The upper index, would that represent the tangent basis vector, and the first lower index represent the dual basis vector?
One has to be very precise when one says this, so I'm going to try to say it slowly. So the gamma, let's look up here. Let's look at the definition of the Christoffel symbol. So let's look at this guy. So what it is, it's, if you look at C, it's the component in the C direction, right? Because it comes with the EC.
Right.
So it's the component in the C direction of the change in the A direction of the B direction.
Ah, okay.
So one has to be kind of careful when one says it.
Yeah, I think I see what you mean.
But I mean, it's something that tells you things about how things change, how a direction changes in a direction, and then the components of that. So one important thing to point out is that these Christoffel symbols are not the components of a tensor. And that's because essentially this depends on the coordinate system. So it's not going to have the same transformation properties as tensor components, for example. But if I remember correctly, you will cover that in the exercise class in 25 minutes or something like that. Okay. So let's just, we have 8 minutes left. So just let's just take an example quickly, and then I will just quickly discuss how it works with when you take the derivatives of dual vectors instead. So the example, I will use my favorite, which is polar coordinates, because we have already looked at this. So for example, we had ER, which was this cosine phi E1 plus sine phi E2, right? So if I take the derivative of this with respect to the r coordinate, well, it doesn't depend on the r coordinate, so this is equal to 0. However, by definition of the Christoffel symbols, this should be RR C EC, and since it's the 0 vector, all of the components must be 0, and this tells you then that gamma RR R is equal to gamma RR phi equal to 0. And in a similar fashion, if you take the phi derivative instead, that's going to be minus sine phi minus sine phi E1 plus cosine phi E2, and that happens to be let's see, it's minus r times E phi, if I did the math correctly. Yeah. So this tells you, no, sorry, I did not do the math correctly. I was looking at the wrong place. It's minus 1 over r. No, it's just 1 over r. So this tells you that since this should be equal to gamma r phi c EC, this tells you that E r phi phi is equal to 1 over r. I'm sorry, not E, gamma. While gamma r phi is 0. So note that I didn't need to do this inner product if I can already express it in terms of the tangent vector basis.
So can I ask a question?
Yeah, sure.
Why r phi?
R and phi are the polar coordinates.
No, I mean it's in the r direction, so shouldn't it be phi r?
Yeah, sorry. I'm getting ahead of myself. So you're right. Phi r. Very good. The reason that I am sometimes going to be sloppy with this is that in most cases that we are going to discuss, it's going to be symmetric in the indices. So for example, it's good that you mentioned, because then we can just look at the definition. So if we look at this derivative, dA EB, if we look at the definition that we had in Euclidean space, this is dA dB acting on the position vector. And since we are physicists, we assume that everything is nice, that these partial derivatives commute, and we end up that is equal to dB EA, which means then that if we look at the Christoffel symbols, gamma ABC is equal to gamma BAC. So what I wrote was just hasted, not wrong. So the last 4 minutes is just about enough to discuss how this works for dual vectors. I mean, we're going to do something similar for dual vectors, but we're not going to have to do it through this entire derivation that we did here. Instead, let us note the following. So we're going to check how the dual basis changes with the position. Now, by the same argument that we had before, I can write this as some BAC times EC. And the question is what this BAC is. And in order to find out what that is in terms of the Christoffel symbols that we have already defined, let's look at the following. So let's look at the derivative in the A direction of EB inner product with EC. Now, this is just the derivative of delta BC, so the components of the Kronecker delta, which are constant, so that's equal to 0. However, I can also use the product rule here. So this is going to be EB dA EC plus EC dA EB. And if we look at what this is just this D. So this is DACB. Whereas this thing, if we remember the definition of the Christoffel symbols, is gamma ACB. So this tells us that that this DBAC is minus gamma BAC. So if you want to take the covariant derivative of a dual vector component, say nabla A, let's use omega, this is equal to dA omega b, and then minus gamma a, b, c, omega c. So if you compare this to what we had for the for the tangent vector components, for the contravariant components, you can see the difference here is that we have a minus sign in this case, we have a plus sign in this case. Are there any questions?
Yeah, on that last equation I have a question about.
Yeah, so this one.
Exactly. So you mean that it's is omega omega b a component of?
No, exactly. So it's the covariant component of a dual vector.
Okay.
So I mean, if we look at it like this, so we look at dA omega b EB. I mean, this is the product rule again. This is dA omega b EB plus omega b, and then dA EB, and then we do the same thing as we did before for the tangent vectors, and we find that this term becomes this term multiplied by EB.
Got it.
Okay, so it's 1 minute past 3. I mean, I'm going to remain here, but I know that you have an exercise class coming up. So if you want to ask questions, it's fine to stay on, but you can also go to the exercise class. So thank you for coming in this these hard times. And we have another lecture planned for Friday, if I don't misremember. Correct me if I'm wrong. Okay, so I will try to edit this video a little bit, and then I will try to put it up on KTH Play and make it available through the homepage once that is done, if you want to have a look again. So thank you for today.
Yeah, thank you.